Welcome to Gymkhana TV. Today we will learn about a very interesting topic, which is blackbody radiation. First I would like to tell you what is a blackbody, how a blackbody is defined. Then we will learn about why it is called black, why the name is black, then body radiation, and what are the characteristics of a blackbody radiation, and then few laws regarding this blackbody radiation. Blackbody is actually a benchmark. It is an idealization concept. In the world there is no body which is a perfectly black body, but there should be a benchmark with respect to which we can describe or we can compare the other body which is at a certain temperature T. A black body is defined, a definition of a black body is that it absorbs all the radiation whatever is incident on that body. We know that if a radiation is incident on any surface, then there will be reflection, there will be transmission, there will be some absorption in the body. If we represent the absorption coefficient as A, reflection coefficient by R, and transmission coefficient by T, then definitely from energy conservation we can write A plus R plus T is equal to 1. Now, if the surface is a perfect black body, or if the body is a perfect black body, then whatever radiation is incident on the surface, everything will be absorbed. That means A is equal to 1. Obviously, we can conclude that for a perfect black body, reflection is 0 and transmission is also 0. This is the theoretical definition of black body radiation. Whatever radiation is incident on the body, that will be completely absorbed by the body. Now see why the name is black. We call a body as black from our very basic concept is that if we cannot see that object, we call it as black. Now, perfect black body is that whatever radiation is incident on the body, it is completely absorbed by the body. So, if none of the radiations are coming out of it, then which we can see visually, then we can tell that visually that surface is black. But maybe there are some other radiations emitting by the object, which may be in the infrared region or in the ultraviolet region. So, black body radiation, this black is visually black. This may or may not be radiation black. Okay. Now, what are the characteristics that a black body radiations will have? The main concept of black body is whatever amount of radiation is incident on the body, that is completely absorbed by that body, then it is called as black body. Now, whatever radiations are absorbed by the body, the whole can be emitted by that body. That means whatever radiations are absorbed by a perfect black body, small I am writing this B dot B as black body, whatever radiations are absorbed by a perfect black body should be emitted. That means a perfect black body is a very good emitter and it absorbs radiation at all wavelength. So, it emits radiation at all wavelength. Okay. And fourth is that the radiation emitted from a perfect black body is a function of temperature only. It depends only on the factor temperature. It does not depend about the shape or size of the black body. So radiation is a function of temperature only. So these are the characteristics of a perfect black body. Now see, we define that black body as a perfect absorber. For it, the reflection is 0. For it, transmission is also 0. So a perfect black body is a very poor reflector. That is also, in that way also we can define, as it is a very poor reflector, so visually it is black. So we call it as black body. Okay. So the next point is that, now how you may think that how then we can make a black body in the laboratory. So anyone from you, can you give the example of a black body which is may not be perfect, that means absorption may not be 1 but maybe close to 1, that is maybe 0.99, 0.98 like that. Anyone from you, can you give the example? Yes, it is lamp black, then platinum black, then gold black. There are few paints which are also close to the radiation emitted from a perfect black body. Some special paints. Okay. Now the question is, in laboratory, how we can make a perfect black body? That can be made. Let we have taken an evacuated chamber, the wall of which we covered by lamp black. Then we make a small hole inside it. If now a radiation passes through this, and it is maintained at constant temperature T. Now if a ray passes through this hole and if it is incident on the surface of this evacuated enclosure, then it will be absorbed by that surface, and we have coated this wall by lamp black, which is taken close to the perfect black body, where absorption is almost close to 0.9. So it can be taken as morally as perfect black body. So the radiation will be absorbed by this body. Now the character of the black body is that whatever radiations will be absorbed, that will be emitted by the body. Now see, now it can be emitted by the body. So it again can be absorbed here, then again there will be emission, then again can be emitted, then again can be absorbed. So the radiation will be trapped within this enclosure. And if there is any radiation that may come from out of this small hole, if we examine this radiation, we will see the nature of this radiation is close to the black body radiation at that particular temperature T. Okay, in this way, in the laboratory, we can make the black body close to perfect black body. Okay. Now, to learn the black body radiation, we should know some basic terms. Like, first is absorptive power. What is the absorptive power? Absorptive power of a black body. Absorptive power of a black body is defined as, it is denoted by A, it is defined as amount of radiation absorbed by the body, amount of radiation absorbed by the body to the amount of radiation incident on the body for a particular time. So as it is the ratio of the same thing, see, it is the amount of radiation absorbed by the body to the amount of radiation incident on the body. As it is the ratio of the same thing, so it doesn't have any unit. This is the definition of absorptive power. Next, there is emissive power. Emissive power. It is denoted by E. What is emissive power? It is defined as amount of energy emitted from the body per unit time per unit area. So what will be the unit of this emissive power? See, it is the energy. We know the SI unit of energy is joule. Amount of energy per unit time, that means second, per unit area in SI unit it is meter square. So joule per second we know as watt. So the unit is watt per meter square. This is the emissive power. Okay. Now there are many scientists who tried to they tried to give some law regarding the radiation emitted from any body. First is Prevost theory of exchange. Prevost theory of heat exchange. How the radiation occurs from a body when it is at a particular temperature T. First is Prevost theory of heat exchange. Heat exchange. Any body, this is a pen, it has some certain temperature. So this body also emits some radiation. But maybe it is not in the visible region, that's why we cannot see that radiation. Maybe it is in the ultraviolet region or maybe it is in the infrared region. That depends what is the temperature of this. Okay. Now, Prevost suggested that any body which is at a temperature T will emit radiation from it, and it also receives radiation from the other objects, from the surroundings. If the radiation emitted by a particular body which is at a temperature T is equal to radiation received from the surroundings, then the body will be at equilibrium. Then the body will be at thermal equilibrium. And if the radiation emitted by the body at temperature T is greater than the radiation received from the surrounding, if it is greater, then obviously the temperature of the body will drop down. Then temperature of body will drop down. And if radiation emitted by the body at the temperature T is less than the radiation received from the surrounding, then the temperature of the body will increase. That is the proposal of Prevost, which is called the Prevost theory of heat exchange. Then we will learn about the Kirchhoff's law. Kirchhoff's law. Kirchhoff suggested that at a particular wavelength and at a particular temperature, the ratio of emissive power to absorptive power of all the substances are same, and that is equal to the ratio of emissive power to absorptive power of a perfect black body. And we know as the absorptive power of a perfect black body is 1, so the ratio of emissive power to absorptive power at a particular temperature and wavelength is equal to the emissive power of a perfect black body, and this constant is same for all the substances which are at a particular temperature T. This is the consequence of Kirchhoff's law. Next is Stiffens law. Now you may think that we have learned that what is absorptive power, what is emissive power, and we know that any surface which is at a particular temperature T will emit some radiation. But how much radiation will be emitted by that surface, that is given by this Stiffens law. Stiffens suggested that the amount of energy emitted from the surface per unit time per unit area, that means emissive power of a body, is directly proportional to the fourth power of its absolute temperature. So as it is proportional, so there will be some proportionality constant sigma into T to the power 4. This sigma is called Stiffens constant. This sigma is called Stiffens constant, whose value is 5.67 into 10 to the power minus 8. See what will be its unit? Its unit will be E by T to the power 4. Its unit is E by T to the power 4. What is the E? E is emissive power that we have already derived, that its unit is watt per meter square, and T is Kelvin to the power 4. So sigma is 5.67 10 to the power minus 8 watt per meter square per Kelvin to the power 4. Okay. Now what is the significance of this Stiffens law? It is that amount of energy emitted by a body per unit time by a perfect black body is directly proportional to fourth power of its absolute temperature. Now let it is a body. It has some temperature. Now it is possible, we can measure what is the amount of energy emitted by this body which is at a temperature T. Let the temperature of the surrounding is T0. So let T0 is the temperature of surroundings and T is the temperature of this body. Temperature of body. Okay. So we can measure what is the amount of energy emitted by this body per unit time per unit area, that is equal to Stiffens constant, then T to the power 4 minus T0 to the power 4, because it is directly proportional to the absolute temperature, fourth power of the absolute temperature. Now its temperature is T, surroundings temperature is T0. So what is the difference? T to the power 4 minus T0 to the power 4. Now why, you may think that why I have provided some space. Now this is the law for a perfect black body whose emissivity is also 1. This is a perfect absorber. Now I will put here epsilon. This is the symbol for emissive power. This emissive power of the body may be this value of E may be 0.6, maybe this is 0.7, that depends on the nature of this body. So the amount of energy emitted by this body per unit time per unit area will be this. Now see, if difference of T and T0 is not very greater, if it is not, then we can simplify this result. See, we can simplify this result in the way, I can take T0 to the power 4 as common. So I will get So T I have written as the difference of the temperature I have taken as T minus T0 is equal to delta T. So T will be is equal to T0 plus delta T. I have substituted that value of T and then it is a simple calculation. It is like 1 plus x to the power n, that is 1 plus nx plus higher order terms. And as delta T is very small, so I have neglected the higher order terms. Then after simplifying, we get the amount of energy emitted per unit time per unit area as 4 epsilon sigma emissivity sigma T0 cube into delta T. That means here the amount of energy emitted per unit time per unit area, if the temperature difference of the body and the surroundings is not very large, is directly proportional to the delta T, which is also the called Newton's law of cooling. Newton's law of cooling. Okay. So now we get some basic laws of reversed theory of heat exchange. That is, if any body which is at a temperature T, it always emits radiation and receives radiation. That is Prevost theory. Then we get Kirchhoff's law, that is at a particular temperature, ratio of emissive power to absorptive power is same for all the bodies at that particular, if they are maintained at a particular temperature T. Then you get Stiffens law, E is proportional to T to the power 4, where T is the absolute temperature of the body. Okay. Now, many times you may have seen that if a piece of iron, if you heat that, it changes its color. Now, if you measure the radiation emitted from the body, you may have seen that if the temperature of the body changes from lower temperature to higher temperature, that means if the temperature increases of the body, you may have seen the color changes from red. Maybe initially you may not see that because it is in the infrared region. Then after a certain temperature, maybe you will see its reddish color. As you goes on increasing the temperature, you will see the piece of iron become blue. After that it is white. Then again you will not be able to see, because that is again in the ultraviolet region, that is which is less than the wavelength of our visible range. The wavelength that we can see is of from 4000 to 8000 angstrom. Within this region only we can see. Below this and above this we cannot see. Okay. So you may think that the energy emitted from a body when its temperature increases will increase or decrease. That means we have two plates which is maintained at temperature T1 and T2. Let the medium between them is vacuum. So only no conduction, no convection is possible, only radiation process is possible. Let energy emitted is E1, energy emitted is E2, and let we have taken T1 greater than T2. Okay. So that means it is at higher temperature, it is at lower temperature. Let us assume that E2 is less than E1. So which direction the amount of heat energy will flow? E2 is less than E1. That means amount of heat energy will flow from this direction to this direction. That means Q is equal to let we have taken T1 greater, so we have taken E2 greater than E1. E2 minus E1. Okay. So Q is equal to E2 minus E1. That means heat energy will flow from low temperature to high temperature, which is not possible from thermodynamic law. So obviously, if T1 is greater than T2, then E1 is also greater than E2. Okay. So first, when gave his displacement law, which states that wavelength is inversely proportional to the temperature of the body. If you plot that, it says that if the temperature of the body increases, if we plot it with the frequency versus the energy, this means that T is directly proportional to nu. If lambda T is equal to constant, that means T is inversely proportional to lambda, which means T is directly proportional to nu. Okay. So if we plot that, we will see that amount of radiation we state that, so if two bodies are maintained at a temperature T1 and T2 where T2 is less than T1, we will see the amount of energy radiation like this, where the peak for this T1 curve is at position of nu1 and peak at temperature T2 is at nu2. So this is the Wend's displacement law. Okay. Now see, look at this graph. What this graph tells? This graph tells that if you increase the frequency at a particular temperature, if you plot the energy distribution graph of a black body at a particular temperature T, you will see with the increase of the frequency, the energy increases. Then at a particular frequency it is maximum, then again it goes on decreasing. It was the experimental result. There was no theory in the late 19th century. Sorry, late 18th century, 19th century. Yes, it is late 19th century. There was no theory. First, when tried to give an explanation using the thermodynamic concept of this energy distribution graph. As it is beyond the scope of this lecture about the derivation of Wend's distribution law, I will just write down the expression and then I will explain it to you. Wend's distribution law, Wend's, now it is distribution law. That means how the energy is distribution law, which gives how the energy is distributed with the frequency. He got the formula that 8 pi h nu cube by c cube e to the power minus h nu by kt. With the thermodynamic derivation, you can derive this, that I will tell in some other classes. When distribution law is that 8 pi h nu cube by c cube e to the power minus h nu by kt into t nu. And here it is energy distribution, that means amount of energy per unit frequency. U nu we have plotted here. Okay, U nu d nu we have plotted here versus frequency. Now let me come on to only to one graph for a particular temperature T. For a particular temperature T. Okay. Now, when he plotted his theoretical expression, he obtained that the graph like this. This is for Wend, and this is the experimental graph. So see, his result match with the experiment for higher frequency range, but it fails to match in the lower frequency range. Then Rayleigh and Jeans, there are two scientists, Rayleigh and Jeans, which is called Rayleigh, according to their name, it is called Rayleigh-Jeans law. They tried to explain the blackbody radiation distribution from classical electromagnetic radiation consideration. They obtained the result as 8 pi kt nu square d nu by c cube. Now when they plotted their expression for the blackbody energy distribution, they obtained the result like this. This is for Rayleigh-Jeans. Though this result does not match with the experimental result, but it has very high importance because it led to the modification of classical electromagnetic theory. Now see why this is the nature of the graph. See here, U nu d nu is directly proportional to nu square because 8 pi k is the Boltzmann constant, T is the temperature of the body, C is the speed of light. All these are constant for the if the temperature is constant. So it is directly proportional to nu square. That means if nu value increases, obviously energy density will also increase. That is why it matched with the experimental result for the lower value of nu. But now see, as the nu value goes on increasing, obviously it will go to infinity from their Rayleigh's law. But experiment shows that at a particular value of nu it will be maximum, and then again it will go on decreasing. They obtained this result from classical electromagnetic radiation. So obviously then Max Planck thought that obviously there is some need to change the or to revise the classical electromagnetic theory. Then he obtained or he explained the experimental result by bringing the concept of quantization. Then Max Planck implement the idea of quantization. We know that heat radiation is some kind of kinetic energy transfer from a hot zone to cold zone. In atom or in case of solid, in case of any solid, the vibration, kinetic energy transfer occurs in the form of vibration. Max Planck first considered that vibrational energy is quantized. It means that it does not have continuous value. It has some discrete value which he took in the form of E is equal to nh nu, where n is an integer. It has value 0, 1, 2, 3, 4 and so on. See, h is Planck constant, which has the value 6.626 into 10 to the power minus 34 joule second. Okay. As this n has value 0, 1, 2, 3, no other values in between 0, 1, 1, 2, like it doesn't have the value like 1.1, 1.2 or 1.05 like this. It has values, so E has values 0, then h nu, then 2h nu, then 3h nu and so on. So it has discrete values. And this assumption was made on ad hoc basis just to explain the experimental result. There was no experimental verification for this concept, but whatever result he obtained, it was absolutely perfect in explaining the experimental result. Okay, now see why people before Max Planck were not able to take this idea, because see, h value is 6.626 10 to the power minus 34. So when you will put this value here, the energy scale is very tiny. It is tiny scale. So there were no instrument at that time which can find the discrete nature of the energy level. Okay. Now how Max Planck derived his law, that I will show through this calculation. So in deriving the Planck's radiation law, his assumptions were the wall of a perfect black body is made of a oscillator, and those oscillators have discrete nature of energy. That means the energies are quantized. That already we have said that is in the form of nh nu, where n can take value 0, 1, 2, 3 and so on. So these are the energy levels of the oscillator. This E0 level, which is actually energy 0, that have the number of oscillators N0. E1 level has number of oscillator N1, E2 level N2, E3 level N3 and so on. So we can find what is the total amount of energy of the black body. So that energy we can define as E0 energy level has number of oscillator N0, E1 level N1. So total energy is E0 N0 plus E1 N1 plus E2 N2 plus E3 N3 and so on. So this is the first type. Then put the value of E0, E1 and N1 can be defined in terms of N0 as N1 is equal to N0 to the power minus h nu by kt. Then again N2 is equal to N0 to the power minus 2h nu by kt and so on. Then there is simple mathematics. Take N0, h nu e to the power minus h nu by kt as common. We will get this term. Then I have defined x as e to the power minus h nu by kt. So we will get N0 h nu x, then 1 plus 2x plus 3x square and so on. This is obviously of the form of binomial expansion of N0 h nu x 1 minus x to the power minus 2. So we get what is the total energy of the system. Again we also can find what is the total number of oscillators in the system? What is that? That is N0 plus N1 plus N2 plus N3 and so on. Similarly, N is equal to N0 plus N1 plus N2 and so on. Put the value of N0, then N1 in terms of N0 as this, N2 in terms of N0 as this and so on. Again take N0 common, we will get this term. Again it is a binomial expansion of 1 minus x to the power minus 1. So we can find average energy of each oscillator. We know total energy of the oscillator, we know total number of oscillators. So what is the average energy of each oscillator? That is E by N. Put the value, you will get h nu by e to the power h nu by kt minus 1. This is the calculation. Sorry. Now, again this part is beyond the scope of this discussion. We can derive it. The number of oscillators per unit volume in the frequency range nu to nu plus d nu. That means, sorry I removed the picture. We plot this nu versus u nu d nu. This was the experimental graph. If we take a range, like we are taking a range nu and we are taking just above nu as nu plus d nu. This range is very small. We can find the energy density. So how we can find energy density? If we know how many number of oscillators are there per unit volume in this frequency range, then multiplying that number by the average energy of the oscillator, we will get the energy density. That number is given by, this is n nu d nu as 8 pi nu square by c cube into d nu. So we get what is the number of oscillators in the frequency range nu to nu plus d nu. So the energy density will become u nu d nu, that is equal to number of oscillators within the frequency range nu to nu plus d nu, that is multiplied by average energy of each oscillator. So substitute the value, we will get 8 pi, multiply these two factors, we will get 8 pi h nu cube by c cube, then e to the power h nu by kt minus 1 into d nu. This is called the Planck's radiation law, which was actually able to explain the experimental graph. If you plot the Planck's radiation law, it will exactly match with the experimental result. In the next class, we will discuss from this Planck's radiation law and we will see how this Planck's radiation law can be implemented to Rayleigh-Jeans law, Well's distribution law, Well's displacement law and Stiffens law. That we will discuss in the next class. Thank you.